Now, the kinetic molecular theory deals with the description of particle behavior at the molecular level. And in doing so, scientists have consolidated the concept of kinetic molecular theory into what we call postulates, or little rules of conclusion based upon experimental proof and so forth. The first postulate is all matter consists of ultimate particles, atoms, and elements. And you can go on to say with specific chemical and physical properties. The second postulate of the kinetic molecular theory says that particles interact by either attraction or repulsion forces. So we have a common-ish understanding, I think, that if you have two attracting particles like the magnets that I'm showing you here, they will attract one another, and certainly these are opposites attract. If I turn one of the, see, it keeps chasing me around there. So like charges will repel and opposite charges will attract. And so the entire world is made up on negatives seeking positives. And one thing I tell students is that if you can boil it down, boil whatever topic you're working with in terms of chemical reactivities down to what positives are looking for what negatives, it really kind of sets the common denominator on the whole topic. All particles are, third postulate, all particles are in constant motion, which includes one or all of three modes of motion. These modes of motion are translation, rotation, and vibration. if you understand the basic terminology in translation, rotation, the application to particle behavior is very easy. Translation is point to point, something moving in straight lines to another point. Rotation, of course, is head over heels, and vibration is oscillation back and forth like that. So if you try to apply to gas phase components, all gases will demonstrate all modes of motion, if you think about it. Liquids are more restricted, so they're not demonstrating all modes of motion to the extent a gas would. And vibration only, so to speak, would be in solids, because rotation and translation are highly restricted, and vibration is still going on with the molecules or atoms that are in that material. Okay? I'm going to have to slip a little above this. The next postulate is that velocity is proportional to the kinetic energy of content of the particles. We'll develop two topics in that out of this, in that if you have a collection of molecules and you heat them up, it is calculated that they will move faster, create greater pressures if they were confined in a container. If you cool them, it'll move slower. So that's a logical issue, but in scientific terms, that means that the speed that the particles are demonstrating is related to kinetic energy. Now, in the real universe, when two particles collide, energy is exchanged in terms of heat loss and momentum loss. Okay? But in the gas considerations in the kinetic molecular theory, we say that the particles do collide. We don't deny that, but we say that they collide without changing their energy content. That is, they are perfectly elastic. Particles, collisions are assumed to be perfectly elastic. That is, sum of all the energy changes is equal to 0. That's all it means. You have perfect conservation of energy as a function of colliding particles. So you don't really take it into consideration. If you took that into consideration, it's way down the road and something that I don't even understand. So I'm not even worried about it. But in terms of the kinetic molecular theory, these are critical to your understanding. I've tried over the years to put together an acronym that makes these easy to learn. What I want to do is show you how the kinetic molecular theory relates to chemical reactions in a collective sense, in a general sense. For any reaction to occur, four events must occur or happen simultaneously. bottom. It's just A plus B goes. Transition state theory essentially means that at a given energy content or an energy position, positional energy of all the particles, the reaction will take place. That's number one. Number two, the activation energy that I'm about to talk to you about is that energy point at which all four reaction factors occur simultaneously. To understand how this issue works, you need to understand what we call a statistical distribution of particle energies. What that essentially means is that in this room, we have a number of particles you're breathing, okay? Would you say that they all have the same energy? No. Some of them are moving faster than others. But if we took the speed of all of them and added them together and divided by the number of particles, what do we come up with? With an average. It's called a root mean average speed. So the particles in here have a root mean average speed collectively. Some are far below, some are far above, but all collectively there is a root mean average speed. We can plot in a statistical distribution of particle energies in a container. That distribution of energies of those particles are temperature dependent, and this is what a Boltzmann distribution would look like. Somewhat like a bell curve, and would go like that. In this room, we see a few particles, see the energy on this axis, on the horizontal axis. There's some that are low energy, and then over here we have some at high energy. And all of them are under an average temperature 1. This point, just draw a little vertical kind of on the end of your curve right there, that passes through the horizontal axis. Well, the point at which it intercepts the horizontal axis is the energy called the activation energy. The activation energy is the EA, if you will. Activation is the energy content that the particles need to initiate a chemical reaction. In other words, this is the point at which all four reaction factors have the greatest probability of occurring, the CENT. This temperature 1 is that you only have a small fragment of particles that will undergo chemical reaction. Anything at the red line or to the right represents reactive particles. Majority of the particles back here do not have enough energy to fulfill the four reaction factors, right? Okay, so what do? You heat. You raise the temperature of your container. How do you cook food? You add heat to it. And it reacts faster. Well, that's essentially what's happening, is that you heat, some of these particles are going to shift to the right at a higher temperature, where T2 is greater than T1. And you can do that, and it will eventually move the majority of them. You can keep heating them, and all of them will be over this red line. Now, when you look at and compare the numbers of particles that have the ability to react now, you've moved from case 1 here to case 2, then up to case 3. You have all of this space here versus the 2 and number 1 space. So to get a reasonable yield of a product, you need to get the reaction at or above the activation energy, and then it will proceed to form products. Reactions in general are characterized to understand the issue and terminology. You have to understand a thing called system and surroundings, which you've probably never been exposed to at this point, up to this point. To explain endothermic and exothermic, I have to go over this idea of heat and energy flow, gaining and losing energy, system and surroundings. T-table. Okay, draw a T-table. On the left side, you want to put system, and on the right side, surroundings. The system is defined as the object of interest. Well, in chemistry, it's chemical reaction. That includes not only the reactant side, but also the product side. Botanists might be interested in flowers, and that includes the entire flower. For a chemist, reactions. Okay. Surroundings is everything else. And I do mean everything else. Here you have a reaction, chemical reaction, with both sides available, reactant and product sides. That's the system. When you leave that drawing of reactant yields products, when you leave that, you have solvent, you have beaker, you have air next to the beaker, you have trees next door, you have the houses across the street, and the stars, and all of everything is receiving from the system, both sides. And so now we're in a position to define endo and exothermic, because endo and exothermic are always defined relative to the system. Critically important that you recognize that. So one of two things is going to happen. What's that system is going to do? And we're going to start here with a system. Here's our system. Right here. So that system is going to lose energy. Now how it loses it, it's business right now. But you just know energy is lost. Where's the energy going? Into the surroundings. Who is in the surroundings? You are. That energy has a language. How can you detect that language? Use a thermometer. Stick a thermometer out there in your surroundings while the system is sending out energy. What's the thermometer going to do? It's going to go up. It's hot over there. No, it's hot in the surroundings. But the system is cooling off, believe it or not. See, you're losing energy. This is losing energy. It's getting colder. But you're standing over here next to the fire. You're the one getting warm. What's getting warm? The surroundings. It's endothermic to the surroundings, but you can't use that relative to the surroundings. You have to use endothermic relative to the system, because here we have an exothermic and over here we have an endothermic. So I can't describe it in terms of both of them, both sides of that tea table. I can't do it. I choose one or the other. So some reactions spit out energy. And you stick a thermometer in there, and whoop, there it is. And you translate that increase in energy in your surroundings to what the reaction is doing. You are the detector, and all your instruments in the universe are receiving the language that reaction is sending you. And there are some reactions, systems that absorb energy. Where's my blue? The system is gaining energy, but the surroundings are losing energy. You're standing in the cold air while the house is warm, so to speak. And you're sending all your energy to put your hand flat on the table. It feels cold. The table is receiving energy from you. That's why it's taking the heat out of you. You're the surroundings. But the system, the table, is going up in temperature. And it'll go up until it reaches a thing called thermal equilibrium, just for if you have a cold room next to a warm room, you open the door, eventually both of them will be at the same temperature. That's all thermal equilibrium. I've got two beakers. A beaker full of hydrochloric acid solution at 25 degrees C. And here's a sodium hydroxide solution over here at 25 degrees C. Okay, about room temperature. I'm going to pour these into this beaker. They will react. HCl will react with sodium hydroxide by double replacement, produce sodium chloride and water. And we'll draw water out like that. So the H is moving over here to the O and hooking up with the O. When you look at the, and over here you have a thermometer. And you start out here at 25 degrees C, and you wind up at 35 degrees C. So the temperature, after you mix the reactants together, before they hooked up, before they reacted, it's 25 degrees. Pour them together in the same beaker and mix them. The temperature of the thermometer goes from 25 to 35. The reaction is the system. But the solvent, the thermometer, the beaker, the air, and everything else is the surroundings. The thermometer, being the surroundings, is absorbing energy and making it go up. That makes sense? If it's part of the surroundings, where's this energy coming from if it's making my thermometer go up? It's got to come from the reaction, both sides. We don't isolate reactants or products. We say the reaction takes place and all of it sends out energy. How do I know? Well, I stuck a thermometer in there and it got hotter. That means the surroundings are increasing in energy. Now interpret what's happening energy-wise to the reaction. It's losing energy. It's an exothermic reaction. So the process that you observed makes this exothermic reaction, and that's how it's characterized. We characterize the reaction or the system, not the surroundings. We interpret what the reaction or system does to the surroundings. We interpret it relative to what the system is doing. You can't measure anything in the system itself. You never do. You always measure something in the surroundings that is sent from the system. When you look into heaven and you see a bunch of stars, okay, is that endothermic or exothermic? You're the surroundings. The stars, the system. Now you can't detect heat changes a bunch of light years from it. But you're a detector. You're detecting light energy as it absorbs into your retinas of your eyes. Thermometer goes up. If you didn't, you'd be blind. So what's the conclusion about the star? Your thermometer went up. What is that star giving off energy? You bet. Giving off lots of energy. You can learn a lot. You can go into the lab and get all your other tools and start pointing it at the star, and you come up with this composition, structure, what's this atmosphere look like, and just go on and on and on. You just got the right tool to receive the language. Yeah, that's the issue of science. The hardest part of science is designing an instrument that will detect whatever you're interested in studying. One and two. Okay, so I want to calculate my change in energy. So that would be the second E products. You can put a PR, products, minus E positional energy of the reactants, which gives me a 25 minus 50, and then put kilojoules down there. It could be calories, kilojoules, just to give it some reality, which is a minus 25 kilojoules. So this reactant to products came out negative based on the mathematics that we just did. And the fact that it shows up negative is indicating exothermic to the system, because this curve matches the system. All right, that's one thing. The second thing is this position right here at the top of the hill is your activation energy. This is the energy. When you reach this point right here, all the particles reach the 4 factors, can achieve the 4 factors necessary for a reaction. This is your activation energy. It is that energy content necessary for all of the particles to have sufficient energy to go through the 4 reaction factors and make products. Okay? This last thing. Okay. There. Okay, now let's scribbly looking. In terms of the system, not the surroundings. Okay, so the reaction is either gaining energy or the reaction's losing energy, and it's described in terms of these graphics. I have two topics to get us out of this entire thing, and I can do this in just a few minutes. There's a couple of equations. Not now. I'll do it at the beginning of next class. That root mean square speed and Graham's law of diffusion. And that comes out of the kinetic theory, and it's very straightforward.